Okay, well, guys, and everybody, thank you very much for joining us today in this seminar about liquid metal batteries. Our speaker will be introduced by Norbert or Tom. Would you do me the favor to introduce the speaker, maybe?
I can say a few words. Thank you. So in fact, the experiments which will be shown, they were performed mostly by Steffen Landgraf. He just switched off his video. And I would say the electrochemists usually, they build closed cells. They put 2-3 cables on the cells and characterize them. But Steffen has studied physics, and therefore he likes to see the cells. So whenever possible, he builds the cells open that you really can look inside to see corrosion or any reaction, that you can see it with your eyes. And therefore we have many of these images. And in fact, I think Michael's his major work was on the optimization of the battery to optimize the shape, how large should it be, the dimensions in general, how to integrate it in the grid and so on. But he worked also on the design of the cells, also helped in the laboratory, and today he will present basically all these results together, but Steffen can then help if you have any questions. And this time I sent the invitation of Alberto also to many other people, and I think if you would like to be invited to other talks, maybe it would be the best to write an email to Alberto. Yeah, and with that, I would hand over to Michael.
Okay. Thank you, Norbert. Can I please ask everyone to switch off the microphones? I have unfortunately lots of feedback here in my stereo. Okay. As Norbert said, I will present today some experiments and visual observations of liquid metal battery cells we prepared in our laboratory. As mentioned, all the experiments were done by Steffen Landgraf, who is also here today and might be helpful in answering some questions later. Just a short overview, what are the main research topics at HZDR regarding liquid metal batteries? We have a large part fluid dynamics, which Norbert is mainly involved in. As he mentioned, the system integration of liquid metal batteries is naturally my part. How to build large-scale systems out of these cells is what I'm looking into. And another big part is the battery laboratory, which I will present to you today. Our lab can be seen here on the lower picture. It's quite a small room, mainly occupied by 2 glove boxes. We have a M. Brown double box, which is naturally filled with argon and allows very low concentrations of oxygen, water, steam, and nitrogen, which helps to conduct experiments with liquid metals, especially with liquid lithium, which happily reacts with all these gases, especially oxygen and water, but it also heavily reacts with nitrogen if heated to higher temperatures. This is also a problem for our glove box. This setup doesn't have a regeneration setup for nitrogen, so this means nitrogen will build up when the glove box is operated for longer times, and this leads to several cycles where we have to purge the gas completely with lots of argon to push out the buildup of nitrogen. The lab also includes a very good camera which we use to observe the experiments. Most of the pictures are from this camera, including a macro lens, because the experiments themselves are much smaller than you would maybe expect. As you can see in the upper picture here, this small white part here is actually a liquid metal cell. Stefan is doing experiments right now. And so we mostly have just several square centimeters to look at where all the stuff is happening during charging, discharging, and cycling these cells. To observe the atmosphere inside the glove box and some reactions occurring in the cells during experiment, there's a mass spectrometer attached with a glass capillary and very high sensitivity, which is used to inspect gas bubbles evolving during some experiments to detect the general atmosphere and to help to identify side reactions which can happen and in most of the time are not wanted during cycling these battery cells. The electrical connection of the cells is done via several Kiesley source meters available in several current intensities from 3 to up to 20 amperes. And we also have a biologic potentiostat, which is able to be used up to 800 milliamperes with a booster up to 20 amperes as well. All experiments are done with a 2 or 4 wire measurement to have a very good sensitivity in terms of voltage, and the measurement is completely controlled by own software programmed in Delphi by Stefan Landgraf. How does it look in detail? Most of the cells, as I said, are quite small. This is due to the fact that most of the lab-grade materials are quite expensive. So each of these cell build-ups is worth several hundred euros, which means we have to be careful using too much material. If we can conduct an experiment with a smaller cell, it will be done. We have several different setups. Either most of these are completely open cells, which means we can look into the cell and observe the 2 electrodes and the electrolyte in parallel. And we managed to install the 2 and 3 layer setup for different cells. 2 layer setup is basically 2 layers of the lower electrode and the electrolyte above, where the 3rd electrode or the 2nd electrode is held by a rod or a nickel spiral as displayed here. And 3 layer would be a complete filling of the cell with both electrodes and the electrolyte using a electrical insulation on the outer diameter, inner diameter of the cell container. These small cells are handled as follows. The cell container itself is made of is a crucible, usually made of stainless steel or other materials like tantalum in the last time. Also possible is glossy carbon. We also had some, as you can see here, crucibles from copper or iron, which could show some, or which have shown some side reactions with the bismuth, for example, and to have a very low reaction rate with the crucible material, tantalum or molybdenum or something like this is preferred. The diameters diameter of the crucible usually is around 30 millimeters. We have some larger crucibles, but as I said, the cost goes up quite fast, and the knowledge you could gain by having larger cells is not that much higher. So we stick to the small cells. The crucible itself is placed on a heating plate. This is a ceramic heater which is temperature controlled from outside the glove box, and around the crucible there's usually a quartz shield, sometimes also a lid on during times of the experiment where visual observation is not needed. This is first to have a lower heat transfer from the crucible to the glove box surroundings, and second to avoid vapors, for example, liquid or then gaseous lithium or gaseous potassium, for example, to contaminate the glove box. If you have higher temperatures, let's say 600-700 degrees Celsius, the light metal electrode will start to evaporate and creates lots of metallic fumes in the glove box. The lower electrode, typically bismuth, or in our experiments, is then filled in the crucible. On top of the bismuth is the electrolyte, here displayed in this light yellow-gray color, and then we lower the other electrode, which is typically contained either in a nickel spiral or a nickel foam, as displayed here, or a similar setup which holds the lithium by cohesive forces, and this allows to be able to operate the whole system without an electrical insulation outside or in the inside diameter of the crucible. There are some 3-layer setups, as I said. There we use alumina or boron nitride or sapphire to insulate the inner diameter of the crucible, which then is only then it's possible to operate the 3-layer setup where we have 3 fully liquid layers on top of each other. As I said, in the heater surface, there's a thermocouple installed, which is used to regulate the heat output of the ceramic heater. The outside of the box atmosphere is cooled, typically to 25 degrees Celsius. It operates between 15 and 38 degrees Celsius. So we have lots of heat transfer from the hot crucible, from the hot electrodes in the cell to the glove box atmosphere. This is shielded by the quartz shield, and this also leads to a high temperature gradient from the bottom of the crucible to the top, and also inside the cell itself there are temperature gradients, so there's always some convection due to different temperatures inside the cell possible. Cathode layer heights are about 2 millimeters roughly. The electrolyte lowest possible usable height is about 4 millimeters. Most experiments use electrolyte layers of up to 10 millimeters. This is to avoid short circuits and to provide a good contact surface between the electrode and the electrolyte. The anode droplet, this lithium droplet here, is usually of a diameter from 3 millimeters to 10 millimeters. You can see when using spirals or foam electrode or current collectors, the electrode itself could be quite large. And there we can use up to 30 millimeter diameter electrodes, which then contain roughly 0.1 mole lithium. Some words on the preparation of metals and electrolyte. Usually we use very high lab grade base materials. For example, bismuth with 9.99% regarding metal traces. This means the related number here is based on metal traces, not on other impurities. So if you melt the new, hopefully new metal, you can sometimes observe lots of other impurities occurring on the surface of the metal, depending on the manufacturer of the bismuth. Typically, the process is to melt the bismuth, let it stay overnight in the melted state, and then to mechanically remove the oxide layer that formed on the surface. It's also possible to use a molten salt to wash the oxide from the liquid metal, and also to use mechanical separation, basically by scratching off the impurities of the solidified metals. Same procedure is for lithium. Here the state how the lithium or sodium is shipped is usually covered in paraffin oil, which has to be removed mechanical by scrubbing it. And then the preparation steps are the same: melting, removing oxides mainly by contacting with salt, fused salt, and also mechanical separation of possible impurities. The salt mixtures are typically prepared in the second glove box. There the steps are to grind the raw salts, solid salts, to store them in the glove box to have a low moisture level, and then there is a heating procedure over several hours up to days to remove moisture mostly. And the vapor contents are measured by the mass spectroscope to get an idea what was included as impurities in the moisture or in the salt mixture. Then after drying, the preparation of the eutectic mixtures is done by weighting, melting, and then adding the higher melting salt to create the mixture, the low melting mixture. And last steps are, for example, vacuum filtering through a ceramic frit to also remove unwanted impurities, hydroxides, and similar. Here also a mechanical separation, manual scratching the solid salt surface to remove impurities is possible. And one comment, the purification, drying, and especially the inert atmosphere around the cell have a very high impact on the operation and the lifetime of the cells we observed. If the preparation and the materials are not very high purity, you could expect the cell to fail within hours of operation due to corrosion by the impurities and different side reactions, which then led to, for example, a short circuit of the cells. A new technology to improve the salt preparation, for example, and also to improve experiments is the here's displayed vacuum oven. This is a new facility which is built up and tested right now. You can see the delivery state several weeks ago here in the lower picture. This vacuum oven can produce a much purer atmosphere due to the ultra-high vacuum, 10⁻⁷ millibars, which then gives impurity levels in terms of oxygen or water, which are several magnitudes lower than the atmosphere in the glove box. And as I said, we will use this vacuum oven to prepare salts, to improve the drying processes of the salt mixtures, and also for experiments and preparation. The vacuum oven itself has roughly 0.5 meter diameter. The recipient, vacuum recipient, is 0.5 meter diameter, and inside the recipient there is an oven with around 100 millimeter diameter, which can be heated up to 1000 degrees Celsius, and also includes a cooling trap around the oven to catch any possible fumes from or moisture from drying or experiments. Also here we included 2 glass windows to be able to have a visual observation of experiments or ongoing processes, and also attached is a new mass spectrometer to observe any reactions or reaction products which occur during experiments. Here I'd like to show you how a typical cell assembly will happen. Here it's a larger diameter crucible, around 90 millimeter tantalum crucible, and I'd like to show just some pictures how typically a liquid metal cell is prepared. First, here you can see a tablet of solid bismuth. This is molten, and typically, if it's fully molten, we wait for a day overnight and check for impurities. As you can see here on the metallic surface, you can already see some impurities, oxides occurring, which then should be tried to scratched from the surface. If the bismuth is fully molten and impurities are gone, the salt mixture is added. Here this is quite at the beginning. It starts to melt here, and there's a big solid chunk of molten salt mixture, which then melts over time. Then there's another waiting step to wait for dissolved gases in the salt to get to the surface and hopefully to leave the salt mixture. You can see here there are lots of small gas bubbles, which can be quite hard to remove from the salt mixture because they stick to the salt surface, also to the bismuth layer surface, and to the crucible, and it takes lots of time to be able to remove these gases completely. Next step is the anode preparation. Here you can see the anode, which is contained in nickel metal foam with a high porosity of 95%. The anode is prepared in a different step where the nickel foam is lowered into the molten lithium, and then we wait until the lithium completely covers the surface of the foam, and then yeah, we have the whole electrode contained in this foam and can then lower it into the electrolyte layer. And then as soon as there is a contact between the electrode and the electrolyte layer, we can measure a voltage and start to do some experiments. The mentioned impurities can be quite disturbing for doing such experiments. Here you can see two different early experiments with different crucibles. On the lower right side, there's a copper crucible was used. And as you can see, this cell was a bismuth sodium cell. And during experiments, the large parts of the crucible were dissolved and somehow formed particles which then covered the surface of the liquid electrode. Yeah, and this is something you do not want. So we then switched from copper to different other crucible materials. Something similar happened with an iron, as a pure iron crucible. Here also some iron ions could be detected. We used LIPS spectrometer for identifying the different constituents of the black or high lighter impurities seen here. We then step by step switched from these cheap materials, copper and iron, to stainless steel and other crucible materials. In the end, the most reliable crucible for testing was tantalum, as I mentioned, which does not react in such a large proportion with the electrodes and the electrolyte. You can see some reaction on the tantalum, but it does not disturb the experiments as these high impurity on the surface would. Another part which has to be handled when operating liquid metal cells is the metal solubility. Some metals, like for example sodium, have a quite high solubility in the electrolyte. Here in the lower part on the left, you can see a sodium bismuth cell at a higher temperature of 500 degrees Celsius. And you can see the large clouds of dark liquid forming here. This is the sodium solution in the electrolyte, which has a quite dark color. And if you observe such a high solubility of a metal in the electrolyte, this typically means the cell will have a high self-discharge rate, as there are free metal atoms available in the electrolyte, which can react then with the lower electrode, bismuth in this case. And this is something to be avoided. For lithium on the lower right, the solubility is much lower. This leads to a much better cycling performance. As you can see, there is some solubility, but it's not as intense as for sodium. The picture or the video on the upper right side shows some effects of evaporation of lithium at higher temperatures. Here you can see some orange fumes forming at temperatures above 500 degrees Celsius, 550 in this case. So it's better to stick to lower temperatures for experiments, because lower temperatures, for example, will have an effect on the solubility of the metal, which will be lower, and will also have an effect on the vapor pressure of the metal, which will lower the evaporation of the metals, for example, of lithium or potassium. Some experiments showed that potassium will be formed when operating such lithium chloride or lithium bismuth cells, which then will result in a reduction of the potassium and also in a reduction of the electrolyte over time. To identify side reactions in the electrolyte, especially change in electrolyte composition. As I said, for example, if you use lithium chloride, potassium chloride as an electrolyte, which is quite common to use, or would be the first choice to use because it's readily available and used in industry as well. Here we observed displacement of potassium in the electrolyte, which led to the change of the electrolyte composition. If you change the electrolyte composition from the eutectic point, this will have the effect that the melting temperature of your mixture will be higher, which means you need to operate the cell at higher temperatures, and you can have problems with crystallization of the electrolyte if you do not maintain this higher temperature. To get an idea of what happens, we try to observe the electrolytes. There were some black crystalline particles forming as well, and to get an idea about other side reactions, for example, with the change in the electrolyte composition, we used iron chromatography to identify the shift in composition during cycling of these experimental cells. Another part, as I mentioned earlier, nitrogen will accumulate in the glove box, and lithium at high temperatures is happily reacting with nitrogen to form lithium nitride, and this will lead to also a slow, we could say, corrosion of the electrode if it's operated in the glove box for a longer time. Other side reactions we could observe were formation of droplets of lithium inside the electrolyte. Typically you would expect the lithium to be formed at the electrode surface directly during charging, but due to maybe metal solubility, we could observe lots of smaller lithium droplets forming as it looked directly in the electrolyte. And the problem here is, as these lithium droplets form and they float in the electrolyte, if these droplets do not stick to the surface of the electrode, you lose first capacity, and second, you will contaminate your crucible, and this could be a potential short circuit starting point if you have conducting lithium droplets here. Another part you could observe in lots of experiments is the formation of gas bubbles at the electrode surface, for example. Here the formation is at the lithium electrode, but as you can see in the lower part, here overnight was a formation of lots of gas bubbles at the bismuth electrode below the electrolyte, and these gas bubbles sticked in the intersurface layer between electrolyte and bismuth and were quite hard to remove, as you can see here, which is also something you would not expect due to the large density difference between the gas and the electrolyte mixture. It was also not clear where these gas bubbles were coming from. Two possible explanations would be there was still a gas solution in either in the metal or in the electrolyte, which then after some resting time was visible overnight. It could also be a reaction product, for example, coming from the formation of hydroxides, but yeah, we could not identify the true nature of these bubbles yet. Other observations we made were, for example, current drops during experiments, which means the electric current measured going nearly to zero from time to time. This was especially at times where the anode surface was covered with impurities. And also something you would not expect is, for example, from time to time we wanted to test a short circuit behavior. Short circuit means both electrodes touching each other directly, and as you can see here, this try to force a short circuit by sticking the whole rod and the electrode inside the bismuth electrode did not work here due to surface forces. It was not possible to have a reaction between the two electrodes in the cell itself. The expected reaction can be seen here, where a solid bismuth droplet is reacting with a liquid sodium droplet. You can see the high reaction heat during the fusion of these metals to an alloy. The bismuth is glowing bright red. If you want to force the same reaction with liquid bismuth, from time to time there was no real reaction visible. The metals had direct contact with each other, but obviously there was some oxide surface or some liquid state. And these are quite strange things you would not expect from the literature and typical knowledge of liquid metals. One part or one thing which you would expect during a short circuit is the formation of the intermetallic phase. If you have a look at the phase diagram, a typical discharge of a lithium bismuth cell would start at the left side of the phase diagram here across a liquidous line, and then from here the intermetallic phase would start to form, typically in form of smaller crystals, and then if you hit the intermetallic line, the whole system would be solid. This is something you usually try to avoid because the intermetallic phase has the two-phase region here has a lower lower diffusion rate for lithium, which means the discharge behavior will be not as good as fully liquid metals. Typically, for a lithium bismuth cell, the intermetallic phase will form at 450 degrees Celsius from 40% lithium in the alloyed electrode. And this intermetallic phase, if it's solid, has a melting temperature of 1145 degrees Celsius. So it's quite hard to remove this solid intermetallic phase by melting. You can only remove it by adding more bismuth to lower the concentration of lithium again. If a short circuit occurs, typically all the lithium is reacting with the bismuth at the surface of the bismuth electrode, forming such a lithium Li3b disk, which is then solid and takes some time to dissolve again. Typically, the cells are constructed, or the amounts of lithium and bismuth in these cells are so that we do not reach the full solid region. It's typically so that we roughly reach the liquidus line here, which means about 40% lithium if we mix lithium and bismuth completely. The intermetallic phase has a density of around 5 grams per cubic centimeter. This should read Le3Be. And this means the intermetallic phase will float between the cathode and the electrolyte, because cathode density typically is around 10. Electrolyte density maybe around 2.5 to 3, and the intermetallic phase is between, so it will stick at the surface of the lower electrode and then led to problems. Potentially, there could be another short circuit if the electrode, the lithium electrode, is not fully dissolved in the lower electrode. And as I said, we not only have a lower diffusivity, but also a lower ionic conductivity, which will lead to lower current densities during discharging. Here, I'd like to show how this could look. These are the pictures I've already shown. What happens when we lower the electrode can be, for example, something like this. During the first contact, you can see lots of very small gas bubbles forming in the electrolyte. This could be a side reaction. Then you will see some change of color over time. Here we have a somehow greenish color of the electrolyte, which over time might switch to a dark red color, and this indicates a solution of the intermetallic phase in the electrolyte, which is also something you usually do not want to have in such a cell. And if the color occurs here, there is a high chance that you formed the intermetallic phase in large amounts. Here we can see this gray-green disk formed directly at the bottom of the electrode. And here we can see almost all the lithium in another experiment. All the lithium from the nickel foam has reacted with the bismuth and formed a large intermetallic plate. And this is something nearly impossible to remove, especially if you operate the cell in a closed crucible. As I said, we have had a large number of different anode formations and current collectors. As I've shown several times, most of the time we use the nickel spiral with a small or large diameter. We also used small nickel foams with a small porosity or with a small diameter of the pores of the foam. That's better explanation. And as I said, here you can see the ceramic insulation and set up for a 3-layer experiment. The thing one thing you will always see is that the electrolyte surface is deformed, as you can see here. And also the surface of the anode droplet here is deformed due to the different densities, which makes it quite difficult to get an idea about the real surface area in contact with the electrolyte. And this makes it also hard to get real numbers for current densities occurring in these experiments. The difference in current you can get from these cells is quite small, even if we have such large diameter coils or such small lithium droplets. The maximum current for short circuit current is almost equal. And this leads to the conclusion that the cathode surface area is much more relevant for maximum current densities. Here we can see a resulting cycling diagram for these cells. The video here was made by taking a picture every 10 seconds, and you can see the cell was operated over several hours with quite large cycle times in between. And we also did some short circuit current tests, which means the current during discharge is as high as possible. You can see here the electrode is completely discharged into the bismuth, and this is a fully reversible process. Afterwards, it was possible to get the lithium droplet to stick to the nickel again. We had most experiments with sodium bismuth cells in the beginning, and later switched to lithium bismuth cells because, as I said, the experimental behavior of lithium bismuth is much better due to lower solubility, and most of the numerical experiments or numerical simulations were also done with the lithium bismuth because there is much more literature available on these electrode combinations. For the large cells, we had discharge currents typically of 1 ampere, sometimes higher. Voltages varied between 0 and 2.5 volts. For charging, 2.5 volts means you have some side reaction occurring already during charging the cells. And as I said, the surface area is quite hard to define because the lithium lithium floats on top of the electrolyte and forms quite complicated surfaces between the liquid lithium and the electrolyte, and therefore typical current densities are a bit hard to transfer to, for example, numerical simulations, but related to the cathode current, to the cathode surface, we had current densities of around 0.01 to 0.3 ampere per square centimeter for typical discharge of the cells. The anode current densities are much higher depending on how you define the surface, up to 10 ampere per square centimeter. Cycling with small SOCs, delta SOCs, so this means small changes in the composition showed no problems over longer times. For deep discharge, as I've shown here, there were often stability problems, and also for very large currents, the voltage was not stable, which meant that there were definitely some problems with the combination of the electrodes. Maybe the electrolyte layer was too shallow. We then switched to tantalum crucibles to avoid influences from the copper and iron crucibles, and the final step is to use closed cells to avoid reaction with the glove box atmosphere. Here you can see such a closed cell, 100 millimeter diameter, made from vacuum components, and here a sketch of a larger demonstrator cell, 200 millimeters, which then will be operated or built in a similar way to the smaller cells. Here we also use nickel foam as displayed left, or a nickel spiral as an electrode holder for the lithium. And yeah, as I said, this will be done by vacuum, with vacuum components. The results from all these experiments are then, for example, used to validate numerical simulations. As I said here, as shown here, Norbert did some simulations of the current distribution and the concentration during charging, discharging. And as you can see, there is a good experiment and simulation are quite good on top of each other. Answer. Similar experiments were done for Solubility convection by Paolo, and I've been using these and other experiments to get ideas on the open circuit voltage, which are then used to get voltage models for the whole temperature and composition. And with such a voltage model, you can also get information about Gibbs energies, enthalpy, entropy, and then use these information to model energy contents, efficiencies, thermal behavior, and in general current and voltage characteristics. And these are then used to model and simulate the behavior of large-scale systems. This is something I am doing mostly of the time. And here you can see a snapshot of our research group in the last year. Some are gone and replaced by new colleagues. And yeah, if you have questions, I'm happy to answer these now. I have 10 minutes left. Just for your information. Okay.
Excellent. Great. Thank you very much, Michael, for such a detailed presentation about the experiments in the facilities. So, Norbert, I think, as you said, we still have time for some questions. If there are questions, feel free to ask. Yeah, please. Someone.
I have a question.
Yeah, please go ahead.
Okay, thank you. You have talked about the cleaning of the bismuth with salt. Which is the way to clean the oxide of the liquid bismuth with salt? What's the way to do this?
Yeah, you simply have the bismuth in a crucible in a molten state or solid state, and then on top you pour the molten electrolyte, molten salt, and this will then remove the oxide from the metal surface. And then you remove the salt again, and then you have a clean metal surface.
Okay, you have to change the salt to put a salt with the oxides out and put new salt in.
Exactly, yeah. The salt is then only used for cleaning purposes and then replaced by the real electrolyte mixture afterwards.
Okay, thank you.
Rainis Paranovich raised the hand.
Hello, I have a question about this. Why do you keep it overnight to prepare it for the experiment?
It was very hard to hear. Could you talk a bit slower again?
I have a question about bismuth. Why do you keep it overnight before preparing the experiment?
The overnight storage is used to have an idea if there is still if there are gases dissolved in the metal, for example, if there are other particles in the metal which are not directly visible. After some time, they will come to the surface of the metal and then are visible, and then you can try to remove it. Yeah, if you don't see it, you have no way to remove it.
Thank you.
Okay.
More questions from the audience, maybe? Very quickly, Michael, did you hit the copper rod before introducing or putting in contact with the electrolyte, right?
Sorry, again?
Did you increase the temperature of the copper rod before putting in contact with the electrolyte, right?
Typically not.
Oh.
No, the point here you can see, for example, the electrode is solid in this case here.
Yes.
The lithium is solid, and you can see a small white ring forming here. This is a solid electrolyte. That's one problem here. We only heat from below, which means there's a very large temperature gradient. On top of this, lithium foam, infused foam, there is almost several hundred degrees Celsius lower temperature than in the liquid electrolyte. So the good point is that the metals are quite have a high conductivity, heat conductivity, which means it will melt quite fast, everything, but there is not a good temperature distribution inside these cells. Yeah, this is also something that will be done with the closed cells, because then we can heat from top and the sides as well and have a much better distribution.
Thank you. More questions from the audience? About using tantalum crucibles will not increase the cost of the battery, the use of this material?
Yeah. Of course, the tantalum crucible is used only for the experiments in the glove box, to be able to have a view inside the cells and to be sure that there is definitely no side reaction. The idea for commercial cells is that the tantalum will be replaced by stainless steel. It is not known of which grade yet, but it will definitely not be tantalum or something similar, because it's much too expensive. Yeah.
We still have time for questions, maybe one more or two more. So, since that. Well, since there are no more questions, so I just would like to thank you again for the detailed presentation, and probably Norbert would like to say something. Norbert, are you there?
Yeah, thank you for the organization, and Michael for the talk today.
Yeah, thank you. But
Great.
pleasure.
Yeah, thank you, Michael, for accepting to participate in the seminar, and thank you everyone for being here today. Hopefully we will see you in the next seminar next month.
Thank
you very much. It was very interesting.
My pleasure. Well, thanks again, guys.
Okay.
Thank you.
Bye.
And have a nice weekend.
Have a nice
You too. Thank you. Bye.
Bye-bye.